benefited from the journey of AI up leveling and interview preparation. And there are the success metrics you can see on your screen, and in terms of compensation. We obviously have some accolades attached to our name, which are flashing in front of you in on the screen. But moving on, this is what you're going to experience today: a sneak peek into the quality of our instructors. So Justin, who is the instructor for today, is going to give you a taste of the high quality of education that we give and during our programs. But obviously, this is a masterclass. Everything is, concise to fit in a certain amount of duration. Certain topics that he's going to talk about in our courses, we cover over a very long period of time so that you can imbibe it properly. I'm going to be back in some time to talk about our programs if you're interested. But before that, I want to know you more. And I'm going to launch a poll very quickly. Use the Q&A section to ask all your questions, and Justin or I will get back to you pretty soon. So without further ado, let me introduce Justin. Hey, Justin, thanks for joining in. Justin is the staff AI engineer at Analog Devices. Like I said, he's joining us from Ireland. He's a homegrown boy, but he shifted to Ireland almost a year back. He did his master's from BITS Pilani. It's been over 10 years that he has been dabbling into various AI roles, and his expertise lies in AI engineering, natural language processing, RAG, LLM ops, etc. Right? So handing it over to you, Justin. I'm gonna stop sharing my screen. Yes, you can go ahead.
Everybody, hope you can hear me. I'm Justin Joseph, and I work as a staff AI engineer for Analog Devices at their European Research and Development Center in Limerick, Ireland. So it's 3 p.m. here right now. So I know it's towards the end of the day at your end. So let's get started with our session today. The objective of today's session is to just give you a high-level overview as to what RAG is, and also to implement a coding notebook, also to support you in implementing a coding notebook in implementing this retrieval augmented generation, which is RAG. The concept of RAG is actually very simple. I'll try to make it even simpler. That's my objective here. So before going into all of that, I'll just quickly give you a brief about what I currently work on. I hope you can hear me properly, by the way.
Yes, we can.
All right, perfect. So apologies about some issue with my throat. So I predominantly focus these days on physical AI. Physical AI means bridging the gap between robotic systems and your software agentic systems. So the agentic systems or the AI systems that we have as software is very capable of decision making, is very capable of reasoning, and then choosing what to do next, what tools to call, how to solve the user's query in the best possible way, all of that. But still, this hasn't translated well into the physical areas. That means the robots still out there are not very intelligent. So we are working more towards developing models for physical AI, particularly uh, aspects that involves industrial automation. And these days, the focus is extensively on dexterous hand manipulation tasks. So that's an overview as to what I'm working on. So I just want to convey the idea that uh, I'm working on agentic systems, RAG systems, LLMs, etc. All right, so let's go ahead with today's session. So the focus of today's session is to give you an idea about what retrieval augmented generation or RAG is about. And in order to discuss RAG, we need to discuss about vector embeddings, what they are, how they help here. We need to look into what vector databases are. I won't be able to go into the complete details of the different vector databases available. I won't be able to compare and contrast them because that requires time. But I'll touch base in such a way that we will try to follow the concept pretty well. That is the idea. And the vector databases that we will focus today are Chroma and FAISS. Some of you or many of you might have heard about it already. And in between, we'll take a break and Niyati will pick this part up. And then we'll focus on building a RAG pipeline. And we are going to use the LangChain, which is a framework for this purpose. So there are a lot of frameworks which you can use to build agentic AI systems or LLM-based systems, LangChain, LangGraph, Crew AI, AutoGen, Identic AI, etc. A lot of it is available out there, and we are going to use LangChain, which might be one of the most popular names out there. All right. So we'll get started with each of the parts. And then after which we'll also take a sneak peek into debugging and optimizing the RAG system, and we'll parallelly go through the demo as well. So the demo that we have is a coding notebook, and in this slides, we have the link to the coding notebook as well. So the link to the coding notebook will be shared to you, or I can just share it right away. I think that's easier. Where exactly is the share button? All right. So this is the link to the coding notebook. You guys can access it from here if you're interested in it. You can do whatever you want with that. It is a Jupyter notebook in Colab, so you can work with it in Colab without installing anything to your system as well. All right. So before we go into the details of all of this, I've been repeating the term RAG. So I need to give you an idea as to what this is. So that is the objective. There are many slides out there. We have like 60 slides. So if I'm trying to focus on every single word written in every slide, this is not going to stop in 1.5 hours or even 2 hours. So I'll focus on the important parts. The primary purpose of why we use RAG is, many of you might be aware of it, is that we need to connect the LLMs that we have. LLMs, for example, the GPT 5.2 or the Llama models, open source Llama models, etc. We need to take these LLMs and we need to make them capable of answering questions about our data. So for instance, if you have your own data, let me just move the slide. So if you have our own data and our data has a lot of documents, for instance, let's consider textual documents, and you have an LLM. For instance, the GPT 5.2 or the GPT-4 or mini, anything. Now, the user comes, any user, it could be you, me, or anybody. A user asks a question to the LLM. And this question is about our product or our data. One moment. Yeah. About our product. So our data consists of details about our product, the intricate details about our product, which might not be publicly available online. Sorry, product. Now, if a user asks ChatGPT, for instance, or Gemini, for instance, or any LLM, for instance, Gemini and ChatGPT are not LLMs, but I'll come to that. So user asks the LLM a question about our product. And assume that it's a very detailed technical question about our product. So the LLM is going to answer based on the data using which the LLM was trained, which is mostly the open source data which is available in the internet. So the LLM obviously will answer. So LLM answers with the limited information available to it. Limited information available. And how was the limited information available? Based on the training data. Based on the data it was trained on. It was trained on. So you might know that LLMs are trained on huge corpuses of data. And these are mostly publicly available open source data or the internet data or the data available on books, etc. Now, the LLMs obviously are going to answer any question that you ask them. Or rarely they might say that I'm not very sure about it, but they'll try to answer. But the real question still remains. Did the LLM answer the question in the best possible way? The answer is no, because it did not have access to our data, which consists of the intricate details about our product. And if this data was available to the LLM, then the LLM could have generated a very good answer. And that is what RAG supports with. So in order to make the LLM capable of answering questions about our data or any additional data beyond which it was trained on, there are generally two ways to handle this. Method number one is to take the LLM and fine tune it, or some people call it retraining, fine tune or retrain on our data. And method number two is RAG. So fine tuning or retraining the LLM on our data. The problem with this is, or the limitation with this is, first of all, you have to know that LLMs are very huge. With respect to the number of parameters, we generally refer to a machine learning model size using something called the number of parameters. So the number of parameters in an LLM is usually huge, probably in billions, trillions, etc. So fine-tuning or retraining such an LLM is going to be a very expensive task. Second thing, when you fine-tune or retrain an LLM, there are some caveats. For instance, I'm just naming it. There is something called catastrophic forgetting. Catastrophic forgetting means your LLM might be very capable at handling certain things like reasoning, for instance. Now, you take the LLM and you retrain it on a data that you have. And in many such instances, there is a risk that the LLM might forget what it is already capable of doing or what it has already learned in the process of pre-training. So the LLM was trained by somebody else in the first place, using huge corpuses of data. After that, if we are deciding to retrain it on our data, there is always a risk that it might forget the capability that it has learned earlier. Or it could be the conversational capability, it could be reasoning capability, it could be creativity, anything. Now, you might face such issues. You might face issues with creating training data or curating training data to perform the retraining. You might face issues with how to perform retraining. You might face issues with the hardware capability of retraining, all of this. So, which is why method number one is not highly sought after, except in specific cases. Now, method number two is RAG. In RAG, so method number one, okay, one moment. In method number one, we will end up modifying the LLM or retraining the LLM. And we have method number two, which is RAG. RAG simply means we will build a pipeline around an LLM where the LLM will be given the most relevant documents from the corpus of our documents, which can help the LLM answer the user's question in the best possible way. So that is RAG. So we are not modifying LLM. We are just providing most relevant documents to the LLM, which can help the LLM in answering the user query. So think about it like an open book examination. I'll come to that, which helps the LLM answer the user query in the best possible way. So think about it like an open book examination. The LLM is our brain. So we are sitting at the exam hall, and if we have an open book examination and the RAG pipeline behaves in this way, so there is a question coming in the question paper. And based on the question, if we have a RAG pipeline, the RAG pipeline will fetch us where the answer to the question is, or the chapter number, or the chapter where the answer to these questions could be. So it can probably return the top 5 chapters where the answers to this question can be. So that part is retrieval. And after the retrieval, we have the question in the question paper. We have the documents of the chapters which are retrieved from our books. And then using the question and using the chapters which are retrieved, we can find the answer. And we can tell that, okay, we can write that this is the answer to the question. So that is how an open book examination works. RAG also works exactly the same way. Now, I'll show you with a flowchart as to how RAG works in a bit more detail, so that you will be able to get a better idea of this. So the most important part is the LLM isn't modified. Only the input to the LLM is modified. So traditionally, the user query is what comes into the LLM. With RAG, it will be the user query and also the supporting documents based on using which the LLM can generate a very comprehensive or a very robust answer. So that is what RAG is. So I hope you got a high level overview as to what RAG is. Now we'll go into the workflow diagram of RAG, which will give you a better context as to what RAG is. Now, I was saying that in RAG, so this is what RAG is about. So I was telling you that in RAG, we have the LLM and the user's query comes into the picture. And based on the user's query, the most relevant documents are fetched. So the user's query goes into the corpus of data, or the corpus of data that we have. Now, from the corpus of data, we fetch the most relevant documents, because the corpus of data can have thousands, 10,000s, millions of documents. So most relevant documents are fetched from that. And then the most relevant documents plus the user query plus the most relevant documents, these many things together are fed into the LLM. And now, traditionally, the LLM would take in the question and try to answer. But here, the LLM takes in the user query and the most relevant documents and then generates the answer. And this would improve the quality of the answer drastically. This is the concept of RAG in a very high level before we go into the details. Generates answer. So the difference between a traditional mechanism without RAG is that user query directly goes to the LLM generates the answer. With RAG, the user query is compared with the data corpus, and after the comparison, we fetch the most relevant documents. I'll come to how this happens. Now, if we fetch the most relevant documents, the user query plus the most relevant documents are fed into the LLM, and the LLM generates an answer. So now the LLM can generate a more robust, meaningful, and to the point answer rather than hallucinating. I hope this part is clear. I know a lot of questions were being asked in the chat, and one was about the pen size. Yeah, I'll reduce the pen size. No worries. So this is how RAG works. But in order to get RAG started, the first thing is comparing the user query with the data corpus in order to get the most relevant documents. So how do we compare two sentences? Or how do we compare two documents? The user query is a sentence or a paragraph or whatever. The data corpus, we are just considering textual documents for now. The data corpus is a collection of documents. Now, how do we compare the user query, which is a document or a text, against other documents, which are the documents present in the data corpus? How do we do that? So the bigger question comes to, how do we compare text? Because we need to compare, since we need to compare the user query with the documents, the user query with the documents in the corpus of documents. So you can't simply compare text, because one text can, you can give the same exact meaning using totally different words in the English language or in any other language, right? You can give totally different meanings using the same words in any language. So the comparison is quite difficult. So how do we compare two text, two elements of text, or two sentences, or two paragraphs? How do we do that? Any suggestions? Semantic search, exactly. So semantic search, yeah, perfect. So the idea of semantic search is that in order to compare text 1 and text 2, I'll call it T1 and T2. It could be sentences, it could be paragraphs, anything. So if we want to compare T1 and T2, we can't just take the words and compare them. We need to convert them to a meaningful numerical representation, and then compare the numerical representations with each other. That is what we always do in the context of comparing unstructured data. Unstructured data can be images, text, audio, video, anything like that. So in order to compare two images, or in order to compare to an image and a text, in order to compare two snippets of text, for all of this, you will be converting your data to meaningful numerical representations, and then comparing the meaningful numerical representations with each other. Now, the process of converting the text or any kind of unstructured data to meaningful numerical representations are known as embedding generation. So text 1 will be converted to, I'll call it E1. Text 2 will be converted to E2. And E1 and E2 are embeddings. embeddings simply mean the numerical representation of the particular unstructured data. In this case, they are T1 and T2, which are the unstructured data, using which we generate E1 and E2, which are embeddings. Now you might ask me, how are embeddings generated? What are embeddings? So to answer what are embeddings are just numerical representations. So you might have heard that this text is represented as a 300-dimensional vector. This text is represented as a 768-dimensional vector, etc. Now, those vectors are actually embeddings. Another name for those vectors are embeddings. So embeddings might look like this, for instance, etc., etc. A collection of numbers that makes no sense to us, but it makes a lot of sense because we are converting the text to numbers. It could be list of lists, it could be NumPy arrays, it could be in any format that we usually use to denote numbers. So embeddings are just numerical representation of the textual data. Now there are a lot of models that are capable of converting text to embeddings. You might have heard of something like Googlebert, Google BERT. So Googlebert is one of the very good embedding generation models for text. It was released in 2018. So it's a language model, and this language model's objective is to generate embeddings or vectors given an input text. So it learns to represent text as a sequence of vectors, and that sequence of vectors is what I was referring to as embeddings. Now, you can use any such models. It could be Googlebert, it could be SentenceBert. There are a lot of models available out there. Now, you can check that. So we will use any embedding generation model, example, Googlebert, in order to do this. Please take note that in order to convert T1 to E1, we'll use a model. That same model is to be used to convert T2 to E2, because otherwise, if you use two different models, then it doesn't make sense, because the conversion of text to embeddings or the conversion of unstructured data to embeddings should always use the same model inside the same pipeline, because you need to compare E1 and E2 in order to know how similar T1 and T2 are. So if you want to do that, then E1 and E2 should be generated using the same method or same mechanism from T1 and T2. So the same model will be used in both cases. Now, the problem that we faced earlier was that we couldn't compare T1 and T2 directly because it was text. But if we have numerical representation of the data or numbers, we can compare E1 and E2. And if E1 and E2 are highly similar to each other, it means that T1 and T2 are very similar with respect to the meaning of them. So E1 and E2 are the embeddings. How do we compare two embeddings? If you go back to your high school classes, you would have learned about vectors. In high school physics, if I remember, it was in grade 11 or plus one. So plus one or plus two, somewhere, you learn about comparing vectors. So you take two vectors, you compare them using some mechanism. How was that? Does anybody remember that? Yeah, exactly. Cos theta, or the distance between the embeddings. The same exact mechanism is what is used here. So I hope you understood why we are converting text to embeddings. We cannot directly compare text, so we are converting text to embeddings. Now, how can we compare these embeddings? Because the comparison of embeddings, whatever it tells us, whatever the comparison of embeddings tell us, whether these embeddings are similar or dissimilar, if the comparison tells that these embeddings are similar, it means that the T1 and T2 from which these embeddings were created are similar to each other. If the comparison tells us that the embeddings are dissimilar to each other, then the T1 and T2 from which E1 and E2 were created are dissimilar to each other. I hope this part is clear. Now, I did tell you that embeddings are multi-dimensional representations of data. You can call it embeddings, you can call it vectors, different literature call it different names. And some other literature calls it sequence of vectors, anything like that. So these are technically multi-dimensional numbers, or you can call it multi-dimensional arrays. So I'll just give you an idea. If you use Googlebert, I think it's the small or the medium variant of Googlebert. If you use it, you're going to get 768 dimension output. Now, if you use some other model like Word2Vec, Word2Vec is a traditional model. If you use that, you will get a 300 dimensional vector, etc. So the dimensionality of the vector, using that, you can plot any embedding in a multidimensional graph. I did tell you that we are dealing with a 768 dimensional vector if you use BERT. Now, these 768 dimensional vector can be plotted in a 768 dimensional graph, which obviously you and me cannot visualize. So for the sake of visualization, we will use a 3-dimensional graph. So any embedding can be populated on a multidimensional graph depending on its dimensions. Now, we have decided to take a 3-dimensional graph just for simplicity, and we have decided to plot our embeddings here. So T1 and T2 generated E1 and E2 respectively. So I decided to plot E1 in the multidimensional graph, and E1 came out to be here. And then I decided to plot E2 in the multidimensional graph, and E2 came out to be somewhere here. Okay, E2. Now, I decided to take one more text, which is T3. And I use the same mechanism in order to convert T3 into E. Wait, I use the same mechanism in order to convert T3 into E3. E3 is the embedding generated from T3, which is T1, T2, T3 are text, E1, E2, E3 are embeddings. Now, I'm populating E3 as well. All right. Now I'm populating E3 as well. So I ended up plotting E3, and E3 came out to be plotted here. Now, looking at this and trying to recollect what you learned in your high school classes, do you think E1 is more similar to E2, or do you think E1 is more similar to E3? Is E1 more similar to E2 or E3? What do you think? E3. So all of you agree with us. So some of you might use angle as the reasoning, some of you might use distance as the reasoning. Either way, I'll just briefly explain it. So you can use Euclidean distance as one method. Euclidean distance. And Euclidean distance simply means the distance between the embeddings. So the distance between E1 and E3 is this. The distance between E1 and E2 is this. So it's very clear that the distance between E1 and E2 is higher than the distance between E1 and E3. Lower the distance, higher the similarity. So the distance is inversely proportional to the similarity. So here, it is clear that E3 is more similar to E1. Now, on the other hand, you can also use another mechanism, which is using the angular spread. So some of you mentioned the cos inverse or cos theta, etc. That's the same thing that I'm trying to convey. So if you decide to go take the angular spread, the angle that E1 and E3 made with each other, I'll call it theta. And the angle that E1 and E2 made with each other, let's call it alpha. So you can clearly see that alpha is bigger than theta. So the higher the angular spread, lower the similarity. So in order to calculate this, I'm skipping a few steps. In order to calculate this using one single metric, one of the most popular metrics that we use out there is called cosine similarity. And if you decide to use cosine similarity, when you run cosine similarity, you need to provide two embeddings as the input. And cosine similarity is going to give you a value between -1 and +1. +1 means extremely similar or exactly the same. So when the value of cosine similarity is more around +1, it means that they are highly similar. And if it is more around -1, it means they're highly dissimilar. So cosine similarity, Euclidean distance, etc. are metrics used to compare the similarity between different embeddings. I hope this part is also clear. So we talked about how embeddings are created. We talked about how embeddings can be compared. Now, if E1 is more similar to E3, like we saw here, then T1 is more similar to T3 compared to T2. This is how you can compare. So we talked about the basic RAG pipeline as to how RAG helps in providing information from our documents into the LLM so that the LLM can answer the questions about the user query by using the documents, somewhat like an open book examination. Now, we also talked about how we can compare text, because only if we can compare text, we can figure out which documents are the most relevant or most similar compared to the user query. So we discussed that part as well. Now, stitching all of these together, we will discuss the RAG pipeline in detail. So this was a good one, good image that I found, which explains the RAG pipeline pretty well. So this is the retrieval augmented generation chatbot architecture. I'll go into the details of this. Now, to start with, I told you that the user would ask a question. Sorry. To start with, we have the corpus of our documents. And assume that we have only textual documents for now for simplicity. So we have the document corpus available with us. Now, in order to fetch which documents in the corpus of documents are most similar to the user query so that we can feed the similar ones to the LLM. In order to do that, you need to convert these documents into embeddings and store them somewhere. So you pass these documents to an embedding model. For instance, the same BERT model that we talked about earlier. And these generates or these creates the embeddings for us. Now, if you have 10,000 documents, you can create 10,000 embeddings. Or I'm excluding aspects like chunking for now to make it look simpler. So you take the documents, you convert them to embeddings. And now you need to store these embeddings somewhere in some kind of DB, in some kind of database, so that if we need to compare a user query against these embeddings, we should be able to. So in order for that, we store them in a vector database. And some examples of vector databases you might have heard of are FAISS, ChromaDB, etc. There are a lot of examples out there. I'm not going into all of them because it would take a lot of time. So FAISS, ChromaDB, etc. You can use embedding vector stores like FAISS, ChromaDB, etc. to store the embeddings. So all of these things that are mentioned in the dotted box, these things are offline. Wait. These things happen offline. That means it doesn't happen in real time. So you might have 10,000, 100,000, millions of documents. So you don't have to worry about the latency in creating the vector DB using this because we are doing it offline. That means we are not doing it in real time. Now coming to the real time picture, the user asking a query. That is the real time picture. So the user asks a question. This is obviously a text which comes into the LLM or which comes into your interface. Now, in order to answer question about this user query, you need to pick or you need to fetch or you need to retrieve the most similar documents which can help in answering the user query, right? Now, in order to answer the user query, you can't simply compare the user query text against the textual documents in your document corpus. You need to convert them into embeddings. Like we converted T1 and T2 to embeddings, here we convert user queries as well as the documents into embeddings. The converted embeddings which came from the documents are stored in the vector DB. Now in real time, the user query comes in, the user query is fed to the same embedding generation model. And then we have created EQ or eQuery, which is the embedding created from the user query. eQuery. eQuery is the embedding created from the user query. I'll just zoom out a bit so I have space to write. eQuery is the embedding generated from the user query. And this eQuery is compared against the different embeddings created from your documents which exist in your vector DB. So eQuery versus edoc1, which is the embedding generated from document 1. edoc2, embedding generated from document 2, edoc3, etc. And then we calculate something like a cosine similarity metric that we talked about earlier. So after which we will fetch the documents which are the most similar after performing the similarity or the semantic search. So the embedding of the query is compared with the embedding of the documents, and we fetch the most similar documents. And where do you think the most similar documents go to? To the LLM, because the user query plus the most similar documents that can help answer the user query is fed into the LLM, and the LLM generates a response. This is how RAG works. So looking into each component, we were talking about the retrieval part. The embedding of the user query is compared with the embeddings of the documents which are stored in the vector DB, and we retrieve the top documents. And that retrieval is the R. or in RAG, we retrieve the top documents. So please note that the top documents that we retrieve are the textual documents, not the embeddings, because we don't pass embeddings into the LLM, we pass text into the LLM. So we fetch the top documents, which is the retrieval part. Now, after retrieving, we create a robust user query, which is known as the augmented user query. And the augmented user query consists of the original user query plus the retrieved top documents plus an optional system prompt. A system prompt is a set of instructions that we tell our application how to behave, how not to behave, etc. So system prompt is a set of instructions as to how to respond to this, what you are, giving some examples of scenarios, etc. So if you're expecting to build a customer service chatbot, we will tell in the system prompt that you are a customer service chatbot. You should behave in a professional way. You should never use expletives. You should never use abusive language. This is how you should behave, etc. Your focus should be on solving the user query. And all of those rules and regulations and restrictions are written as text in system prompt. So using these three things, we create a combined input or an augmented input, which is the augmentation part. And then using that, we will trigger the LLM and the LLM will generate a response. So the difference between a traditional mechanism and a RAG mechanism is that traditionally user query is used to trigger the LLM. LLM generates an answer with whatever limited information that it has or it has learned. Now that is conventional chatbots. Using a RAG architecture, you are retrieving the most familiar documents from the corpus of documents, which can help in answering the user query in the best possible way. Using which we created augmented query. Using the augmented query, the LLM is triggered and the LLM generates a response. So this is the RAG architecture. I hope this part is clear. Any questions on this? So if you have any questions, please ask in the Q&A. And I hope we have a TA in this session. If there's a TA in this session, if you can answer the questions, that would be great. So I think they're answering the questions parallelly. That would be great because we have a sizable cohort, like 430 people. So if I stop and wait to answer the questions, it's going to take a lot of time. So toward the end of the session, we can have questions as well, no worries. So this is the idea of the RAG architecture. I just wanted to keep it as simple without going into the details. Like there are a lot of other aspects like chunking, re-ranking, tokenizing, etc., which I haven't gone into. I just want to keep it as simple as possible so that everybody understands irrespective of their level of proficiency. Okay, perfect. So I did tell that we had some slides to cover. I condensed all of those into this so that most of those topics can be covered using a few images rather than and annotations rather than the slides. Okay. Now we will also obviously, yeah, we'll also be looking into the code. Don't worry about that. So meanwhile, let's take a look at the slides and then let's cover the slides and keep going ahead. So the purpose of RAG, why we use RAG, so that we can get better accuracy, we can have dynamic knowledge. Yeah, that's important. So you have a document corpus. Your document corpus can keep on changing in real time, right? Tomorrow, your document corpus might change. If you're looking at product information, some products might be removed, some new products might be added, etc. So this is highly scalable. RAG is highly scalable because you can update your vector DB using the new embeddings of the new products. Absolutely. And it is quick as well. And if some products are removed, you can remove the embeddings corresponding to those products from the vector DB. It's very simple. You don't have to mess with your LLM in any way. But if you were going with the LLM fine tuning, the problem was that you would have to fine tune your LLM based on the change in the data. And fine tuning LLM takes a lot of time. It's not something that I can put for 2 hours and it'll give me the fine tuned LLM. No, that's not the case because LLMs are huge deep learning models. And also, LLMs are RAG can help with domain expertise because if we have data with respect to the particular domain, it can really help in answering the questions relevant to that particular domain. Now, the idea behind RAG we discussed in detail. What is the idea behind RAG? The user asks a question, there is a knowledge base, the prompt is enhanced. That means augmented prompt. User query, the fetched top relevant documents, system prompt using to trigger the LLM and the LLM generates a response. Now, there are many methods to improve RAG or improve the system that we are creating with RAG. So you can have multi-shot prompting. So you can provide better system prompts. You can have better prompting strategies in order to improve this. You can incorporate tools with your LLMs. Okay, I have a quick question for you. This is a question that I ask almost all the time. Do you think ChatGPT, Gemini, etc., do you think they are LLMs? ChatGPT, ChatGPT.com, Gemini, Gemini.com. Do you think these are LLMs or do you think these are something else? Okay, some of you are saying that they're LLMs and some of you are saying that it's not LLMs. And the answer is that it's not LLM. So when you open ChatGPT, you have the provision to choose what model you want, right? GPT 5.2, GPT 5.0, GPT-4 or mini, etc. Those models are your LLM. ChatGPT is not your LLM. ChatGPT utilizes the LLM to build something on top of that, which is called an agentic system. And why do we say that ChatGPT is not an LLM? So I'll tell you this. If you were using ChatGPT back in 2022, around the time that it launched, you ask a question like, what is the weather in Bangalore today? It will say that I cannot answer that because I'm trained with data only up to 2021 September or something like that, right? Now, that is an LLM. An LLM is not updated every day. An LLM is not regularly updated with current real-time information. So, ChatGPT is not an LLM because if you ask the question about the weather in Bangalore right now, it is able to answer it, indicating that it is not an LLM, but rather it's an agentic system. And the question comes, how can ChatGPT answer that? ChatGPT can answer real-time questions like weather questions, for instance, using some tools that it has access to. Like, for instance, the weather API, weather.com API, or Google search. I think Gemini uses Google search, ChatGPT uses weather.com API. I'm not exactly sure, but I'm very sure that it uses tools. So using the tools, you have the LLMs and you have the tools as well. So LLM is the brain. Tools are like your hand and legs. So the brain can decide to use the hands and legs whenever necessary in order to complete the task that it has been assigned to do. So if the user asks, what is the weather in Bangalore? The LLM thinks, okay, do I have enough information to answer this question? No. Does any of the tools that I have can help answering this question? Yes, there is the weather.com API. So let me just trigger the weather.com API using input, which is location Bangalore, date 13th of August 2026. And we trigger, and the LLM triggers the tools, the tool, the weather.com API. The weather.com API returns the response saying that it's sunny or whatever it is. And then the LLM curates a final polished answer for you and gives back to you. So that is the meaning of tool integration. LLM by itself cannot answer real-time questions or such questions that require additional information which can be fetched from some tool like weather.com API, for instance. So tool integration, additional context, you can incorporate all of this to make your RAG system more robust, or in other words, to make your system more agentic in nature. Okay. Now, you can have a knowledge base, and in your knowledge base, so in the example that we are going to do today, we have a knowledge base structure. Knowledge base is simply documents, and those knowledge base structure consists of company information, contract information, employees information, and product information. So this is the this is the repository where we have the data. One moment, elevation knowledge base. So this is the database that we will use for today's code. So you know that for creating a RAG system, you need a database in order to create the embeddings from this. So the database that we are going to use is this, which consists of information about company, contracts, employees, and products respectively, which is shown here. And using this, we will create the embeddings and they will be stored in a vector DB, and then we'll go ahead with the RAG pipeline creation. Okay. And then, if you remember, we were talking about the system prompt as well. So system prompt is a set of instructions that we tell the LLM how to behave, how not to behave, etc. So the system prompt that we'll use is this. You are an expert in answering accurate questions about Insurance LM, the insurance tech company. Give brief, accurate answers. If you do not know the answer, say so. Do not make anything up. So we are asking it to be grounded. We are asking it to use information which is only available from the data that we are providing and not to make anything up. So this is just an example of a system prompt. You can have your own system prompt. All right. Now, there's a quick question. In a RAG system, why do we retrieve document chunks before generating an answer? Option A, to reduce the number of tokens in the question. Option B, to help the model answer using external knowledge, which is not stored in its parameters. Option C, to make the embedding size smaller. Option D, to convert all the text into SQL queries. Which one? A, B, C, or D? I really hope everyone says B, because we were discussing RAG in detail all this time, and we were discussing that the purpose of RAG is to help the LLM generate answers based on external data that we have, which is exactly option 2 or option B, to help the model answer using external knowledge base, which is not stored in the parameters. Parameters means which is not stored in the training information of the LLM. That is the meaning of that. All right. So it's option B. Now, today we talked about vector embeddings. We actually covered this. We talked about vector embeddings. We talked about what RAG is, and we will also talk about what are some popular vector DBs that you can use. All right. So we talked about vector embeddings already. These are the same E1 and E2, which were created from T1 and T2, the same thing. Vector embeddings are just numerical representation of unstructured data like text, images, audio, video, etc. In the RAG pipeline, we are going to obviously convert any such unstructured data into meaningful embeddings so that we can compare the embedding of the user query with the embedding of the documents that we are creating. And the embedding of the documents that we are creating are going to be stored in a vector DB, because we need to compare the embeddings with the user query's embeddings. So the user query will keep on changing, but our vector database will be the same as long as the documents that we have do not change. If the documents change, the vector DB will be updated accordingly. All right. All right. So in our example that we are going to do today, we are going to use the OpenAI embedding generation models. OpenAI has LLMs. OpenAI also provides embedding generation models, and OpenAI's embedding generation models create embeddings of 1536 dimensions. And if you remember the BERT model, if you use it, it creates an embedding of dimension 768. Different models, different dimensional output size. Okay. Now, I covered this aspect by comparing the spatial distance and angle between the two embeddings generated from text. I'm not going into this, but if you're interested in knowing more about this, I would recommend you to read about Word2Vec. I would love to explain this, but I don't think we have enough time for that. That's why. So please read about Word2Vec. Word2Vec, I think it was released in 2015, if I remember right. This was one of the uh, stepping stones in creating the embedding generation setup that we have these days. All right. Now, yeah, we talked about the complete picture. Convert the user query into vector, which is eQuery. Search the vector database. That means the user query versus the embeddings of each document. And then fetch the most relevant documents, which is the retrieval. So if you figure out that the most relevant documents are document number 10, 20, 30, etc. So that will be fetched. Document 10, document 10, document 30, and this will be added to the textual user query along with the system prompt, and that is used to trigger the LLM. So in this example today that we are going to walk through, we'll be using LangChain, and why we use LangChain is because we need a framework. Otherwise, we'll have to code everything from scratch. If you have a framework, a lot of this will be taken care of. You have inbuilt functions to create embeddings. You have inbuilt functions to add it to vector DB. You have inbuilt support to retrieve all of this. So the idea of LangChain is that you chain the different components together. You have a retriever, you have a generator, you have a system prompt, all of this one by one, you will chain it together in order to create your complete picture. Now, The advantage and disadvantage of LangChain is that advantage is that it's very easy to start with. It's very beginner friendly. You have standardized drag workflows and you have model agnostic wrappers. That means irrespective of what LLM you want to choose, it won't have an issue. And also it'll be just a few lines of code. And there are the disadvantages are that from a production perspective, I'm being honest here, from a production perspective, LangChain has many disadvantages, which is why when you look at production workflows, you might mostly see LangGraph than LangChain. So all of those details we will cover in detail in the IK curriculum. Don't worry about that. But here we have a limitation of time, which is why I'm trying to uh, superficially name drop this. So if anybody is interested, you can go into more details of these. Now, all right. So in the LangChain process, in today we'll be using a directory loader. You will get a better idea when we go into the code. So directory loader loads all the txt files that we have from the specified folders. We have 4 different folders. You go into each of the folder, you have the txt or the md files, which will be used to create the embeddings. And then you can also add additional metadata. Your vector DB can store your embeddings plus additional metadata. Like for example, this embedding came from this particular document, or this embedding came from document number this embedding or this document was in this folder. All of these are additional metadata. You can choose what metadata that you want to add. So you can optionally add metadata. And from these, we create document objects. Document objects comprise of embeddings, which are predominantly used in the semantic similarity search and metadata as well. If you need to perform, so if you need to compare, if you need to do anything like a string-based comparison or something, where you want to check about data which talks about only the company information. If this folder name is stored as a metadata, then you can perform a string-based comparison as well, because that will be a part of the metadata then. The choice of what to add as a metadata is totally on you. All right. Now, there is something called chunking. The idea of chunking is that I was telling that we create one embedding from one document. What if the document is very big? So LLMs do not have the capability to take an unlimited length of document, right? Or a document which is huge. Even when you use to trigger ChatGPT will say that, okay, I can't process such a long document or something like that, especially the older variants of ChatGPT. So there is always a context length. So in order to factor the context length into the picture, what we do is we decide to split our document into something called chunks. And this is known as chunking. There are a lot of different chunking strategies available out there, and we'll be using one of the most popular chunking strategy, where this is known as overlapping chunking. So the idea of overlapping chunking is that you have a document. I'll talk with respect to page numbers so that you understand it easily. So page numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, etc. Now, if I decide to perform a chunking in such a way that one chunk can be 4 pages, then our initial thought would be this is chunk number 1, pages 1 to 4. This is chunk number 2, pages 5 to 8, etc. But there is a problem here. Each chunk is considered as a separate embedding. So when you retrieve, if the first chunk, which is chunk number 1 here, if the first chunk has the highest similarity, then chunk number 1 or the document part or the text part of chunk number 1 will be fetched and fed into the LLM. Now, this is fine, but there's a problem. What if the best answer that you could generate was in pages 4 to 5? So between 4 and 5, we did the split. What if the best answer was in pages 4 to 5? So to mitigate such issues, we use an overlapping chunking strategy. That means instead of chunk number 2 starting from pages 5, we can have an overlap such that how to perform the overlap is totally up to you, such that we will have an overlap like this, for example. So chunk number 1 is pages 1 to 4, chunk number 2 is pages 3 to 6, and chunk number 3 can be pages 5 to 8, and chunk number 4 can be pages 7 to 10, etc. This is right thing here, pages 7 to 10, etc. So when you do this, the advantage is that if your answer is lying between pages 4 to 5, even that will be captured well because that belongs to chunk number 2. So this is the concept of overlapping chunking. And if you have proper chunk size with respect to the LLM that you're using, with respect to the embedding generation model that you're using, if you have proper chunk overlap mechanism, then you can even feed huge documents into the corpus of data. So chunking is simply splitting huge documents, and how you can do that, you can use an overlapping chunking strategy, which works pretty well. Now, you can, in our example, we are going to use OpenAI embeddings. I already told that OpenAI embeddings consists of 1536 dimensions. Given a text, it is going to generate an embedding which has 1536 dimensions, and which is very good at understanding semantic meaning. And why are we focusing so much on semantic meaning? It's because the same words can mean different things in different contexts. For instance, if I'm saying that I'm walking to the riverbank to catch some fish, then the bank that I'm talking about is the riverbank. Now, I give another sentence. I'm going to the bank to encash a check. So I'm talking about the financial bank. The words were the same, riverbank, financial bank, but the context is totally different, which is why semantic meaning is very important. We need to use the words around that area or around that sentence or around that particular word. The words which are in the neighborhood of this determines the semantic meaning. So which is why embedding generation models are trained to create very good quality embeddings depending on the semantic meaning. So these two sentences, even if they consist of the same word bank, they'll be very different in the embedding generation process. So even an E2 will be far apart. Just wanted to let you know the importance of semantic meaning. Now questions. If two text passages have similar embeddings, what does that usually mean? They have exactly the same words. They're stored in the same database row. They are likely similar in meaning. They're created on the same day. Which one? See, we are all clear about that. So the idea of dimension. So you were asking the idea of dimension. So if you want to easily understand that, what I would say is consider dimension as one floating point number or one integer. So when somebody says that your embedding generation model generates an embedding of 768 dimensions, just think that given a text, it is going to generate 768 numbers. Okay, so that's the easiest way to think about it. There are further details to it. I'm not going into the details of it, but for now, just think about the numbers that it generates. All right, so this one is C. Now, the two vector DBs that we are going to compare in this process, that will be Chroma and FAISS. There are a lot of vector DBs available out there. It is not limited to Chroma and FAISS. There are a lot of them available, but we'll just talk about the different vector DBs that we have here. And the vector DBs that we have here or that we'll be talking about today are Chroma and FAISS. So both of them are very good for semantic search. Both of them are very good to act as a vector DB. Both of them are widely supported. So in order to create a Chroma DB, what you can do is you can use the Python package of Chroma, and you can use Chroma from documents, and you can pass the chunks, which is the textual chunks. You can pass the embeddings corresponding to the chunks which you already created using models like OpenAI embeddings or BERT or whatever. And then you are simply making the idea of this is that in one line of code you can create the embeddings. So we are converting all the chunks we are creating to vectors. So in our example that we'll walk through today, how many chunks were there? One moment. Printed that. But yeah, we are creating 413 vectors with 1536 dimensions. 1536 dimensions because we are using OpenAI embeddings, and we are creating 413 vectors. And these 413 vectors can be stored as embeddings in the vector DB, which is the Chroma DB. Now, we can visualize high dimensional vectors. The limitation with our eyes is that we can visualize only up to 3 dimensions. But if you want to visualize multi-dimensional vectors, we should have to plot them in multi-dimensional vector graphs. And in order for visualization purposes, we will use something called TSNE, which is the key distributed stochastic neighbor embeddings, in order to project the 1536 dimensional vectors into 3D space so that we can see it properly. All right. Now, each color represents a document type showing how semantically similar the content is naturally clustering with each other. So we'll look at the Jupyter notebook or the code in order to see this better. So you will have to wait until that. Now, the different clusters. We have employees, we have contracts, we have company, and we have products. So each of them refers to different aspects. But if the user query is about anything involving any of these, then the most relevant documents are going to be fetched, which will trigger the LLM. Now, an alternate vector store to ChromaDB is FAISS. FAISS is Facebook AI similarity search. But what I've seen in production is ChromaDB is used more than FAISS, but for prototype purposes, FAISS is widely used. And the advantage or disadvantage, you can call it either ways, of FAISS is that the vector DB is created in memory. That means the vector DB resides in your RAM. So you might not want it all the time because if your data is huge, you might want to save it somewhere and you might have to automatically load it rather than storing it in your RAM. So that could be considered as an advantage or a disadvantage. In-memory storage means it is going to be fetched faster. That is an advantage. Now, FAISS also supports CPU and GPU variants. If you have a GPU, it can utilize the GPU in order to perform the similarity search faster in order to store it using the help of GPU. And there is a minimal code changes required from ChromaDB in order to utilize FAISS if you require. So we just touch based on two different vector DBs. One is ChromaDB, another is FAISS. Now, it also follows a similar syntax: Chroma from documents, FAISS from documents. So the purpose, the vector DB creation and everything is using pretty much similar reusable code in both the cases. So it's very easy to switch between the two different vector DBs that we just talked about today. It doesn't mean that if you are using a totally different vector DB, it will be similar. So if you're using something like Pydantic, if you're using something like Milvus, for instance, it's a different vector DB. It might not be as simple as to migrate to Milvus, just letting you know beforehand. So the question, what is a vector DB mainly used for? You might know this by now. Vector DB is used for what purpose? So I think we are getting mixed response here. Obviously, our objective is not to store numerical data like spreadsheets. That is not the case. It is for semantic similarity purposes. So vector DB's primary objective is this: efficiently finding items that are semantically similar to a query. If our objective was to only store the numerical data somewhere, we could use a SQL table. Why did we even talk about a vector DB? Vector DB's primary advantage is quick retrieval, quick and efficient retrieval. That means you want to compare user queries embeddings with the queries in your vector DB. It'll happen very quick because it uses some mechanisms. If you're interested in reading, I would recommend you read something called approximate nearest neighbor search. ANN, approximate nearest neighbor. So that is the mechanism that most vector DBs use under the hood. I'm not going into that in the interest of time, but the primary purpose of using a vector DB is to efficiently find items that are semantically similar to the user query. And we are not replacing all databases in an application. We are not converting raw text into answers. We might be converting raw text into embeddings, not answers. So it's option 2 or option B. Why might a company use metadata filters in a vector DB search? So I told that you can give additional metadata in your vector DB other than the embeddings. So you can create embeddings for each document. One metadata can be what folder did we create the metadata? Did we create the metadata from? Company or contracts or employees or products. Another metadata can be the length of the document, whatever. It's your call as to what to be a metadata. So what could be the reason as to why a company uses metadata filters in vector DB search? I think this is also quite clear, right? It is option B, to search only within a relevant area or a relevant subset, such as one product area or one document type, for instance. You can perform such limitations, or you can limit the search to such kind of data if you have proper metadata created. Now, that's the answer to that. All right. Niyati, do you want to take over for a moment now?
Yes, happy to. I was your pseudo TA today, so I've tried to answer the questions to the
Thank
best
you
of
very
my
much.
ability. But some of the questions I've
Really
left for
helps.
you because they were very situational, and
No worries, I can take it up. Yeah.
sure. So I'm gonna go ahead share my screen. Yes, hope everyone can see my screen and can hear me clearly. Just check. Okay. I launched a poll at the beginning of the session when I was handing it over to Justin. Just a yes in the chat if you can see my screen. Yep, thanks. So, and I launched a poll to ask that what are your career goals for this year and what is stopping you to achieve those career goals? About 58% of you said that you want to upskill in your current domain, but upskill with the latest Gen AI agentic AI skills, right? We get that quite usually because most of you are experienced tech professionals, right? And nobody wants to start from scratch. You want to layer it, you want to layer your current uh, technical know-how with the right AI skills, and that's the right way to approach it also. Quite fair. But what's blocking you was the next question. And 52% of you said that you do not have a structured roadmap. Or 27% of you said that I don't know what are the right AI skills that I have to learn. And because of that, you could be in any of those four stages of AI denial. That especially those 27% would be feeling something like AI is moving too fast for me. I don't know where to start. I don't know if I've covered enough. There is too much out there, right? In the second quadrant, as you can see. You may feel there's every day something new coming up. How do I know what I'm learning is going to be relevant? It has longevity. It is going to be asked in the interviews. And do I know the exact depth of that topic or not, right? Nobody's kind of benchmarking it. Third, people earlier used to feel that I think that, last year or something that their job is too unique and safe, but now everybody knows that there are AI use cases across. And the biggest reason why people kind of get stuck or they feel stuck is they feel that I have to down level because you might have put 5 years, 8 years, 10 years, 20 years in developing a deep expertise in technical domain that you're currently in, and you don't want to start from scratch like I mentioned earlier. And all of these four are fair, and all of these are the best news is that they are solvable, right? So let us take it from the beginning that about 3 years ago, AI was all about increasing your productivity. It was all about augmenting your work, right? But in the last 1 year or so, or maybe 1.5 years or so, it has all become about transformation. Using the right AI skills to transform your current processes, to transform your current models, or build new models, or build new complex apps using agentic AI and Gen AI, right? And now it has become table stakes. Having the right AI quotient for your job or for the next job that you're planning to do or for the next promotion even, having the right AI quotient is very, very important, right? And I spoke about customization earlier at the start of the whole session, and I'm going to touch upon that very soon. We have about 3 programs that we cover, and to quickly tell you, to reach the right AI role that you want to, there are these 3 paths for you available. I have not put all of these three together to confuse you, but I've put here to tell you, for example, if you're unsure, right, you don't know where to start, you can basically start with this. So there those 52% people who said, I want a structured roadmap. This is the structured roadmap that you were looking for. The 57% people in the first question who said that I was I want to layer my current tech stack with the right AI skills for my tech stack, this first program is for you, which is Transformative Gen AI and Agentic AI plus Interview Lab. Here you go from, obviously, it is customized in 18 domains. Some of the examples are written over here, so I'm not going to repeat them, but there are 18 role tracks that we cover. We take you from beginner to advanced level of agentic AI skills, from Gen AI to building agents to multi-agent system. And every week you're doing projects. And by the end of the 11th week, you're doing one big capstone out of it, right? You can choose your track. You can choose a pro code track, a low code track, or a no code track. Now, everybody has different proficiency in coding, and we understand that, right? So you can choose a pro code if you are from, say, SWE background or a data engineering background. No code if you are from a product management background, right? Or a data analyst or business analyst background. You also get opportunity with our instructors like Justin himself, get an opportunity to perfect your interviewing giving skills, because interview lab is also part of this program. 15 mock interview opportunities to perfect that interviewing giving skills, especially in the age of AI, right? What are the kind of questions that are people asking? What is the proficiency in AI that the employers are expecting, and how do they expect you to reason it out in interviews? Apart from that, of course, the capstone that I mentioned, you can even bring your own project and we can help you with that, right? Now, if you already have a certain proficiency in coding, for example, you can write Python code, and you have some base of AI knowledge, like some people in the audience already had that, we have a program which can help you develop a portfolio that signals the employers that you have the right know-how of AI. Now, these, mind you, are case studies, industry specific case studies that are given by PwC India to us, and in BFSI, e-com, supply chain, and in healthcare. And you can complete one or four of the capstones and develop a portfolio of agentic AI projects. Plus, in this also, we cover the interview lab. And hence, again, I will explain what all we cover in the interview lab in detail in the next slide. But here also, we prep you for the kind of roles you are targeting. Now, the newest role in the market, which is the forward deployed AI engineering, is seeing a massive growth. In India specifically, US, it's about year and a half or so old, and India, it's massively coming to us, and more companies every day are hiring for these for this particular role. Now, this is engineering and customer, it's a mix of engineering, AI engineering, customer know-how, and solution architecture, right? So who is it meant for? Who can do it? About eight out of the 18 domains that I mentioned, 14 can actually go ahead and do it. Some of you already have certain capabilities that one needs for to become an FDE, or a forward deployed engineer, right? And this is actually the most in demand at this point of time and seems to be the future, because AI has kind of faded away the lines between customer and tech, right? Or business know-how and tech. So combination of that makes you a really, really strong engineer. So what do we cover here? We cover AI engineering, we cover the FDE craft, and we also cover FDE interview preparation. You will do this is a 23-week program, has 4 phases, like I mentioned: AI engineering, vibe coding with Claude, FD, Spine, and interview preparation for FD. Mind you, this combination currently you do not have in India as of now, this particular combination of modules that I spoke about. So if you're really interested to augment your career as an engineer, and and you already understand the potential of FD role, close your eyes and go for it. It's the latest program that we have made, and we have already seen a lot of enrollments. Mind you, parallelly at the same time, we have the FD masterclass going on. So if you want to join in, we host it every week, so you can join in the next Thursday itself. Now, to come back to what do you do in in interview preparation and career services? We customize it for all of these 18 roles that you see in front of you. If you see a role, especially the transformative generative AI and agentic AI plus interview lab program, and any of our interview lab is customized for these 18 domains. Of course, the FD is not, because you're transitioning into an FD role itself, right? What do we cover in our in our career services and our mock interviews? These mock interviews, like I said, are live with our instructors. They are the ones actually sometimes the hiring manager for most of the positions in the market, because like I said, they are the ones scaling AI systems in their company, so they can actually tell you hear it right from the horse sort of a thing. And we, apart from that, cover DSA, system design, and the domain specific, the domain that you come from, domain specific modules also. The career services, of course, in addition to all of this, uh, uh, we give you LinkedIn optimization, we help you with resume optimization, we help you negotiate your salary, crack those rounds, because that's also difficult. You don't know how much, once you have AI skills, how much should you ask for from the employer. And those are benchmarks that we have with us. Behavioral rounds, right? Because while you may ace the skills, but you also need to ace the behavioral rounds. Now we don't leave you high and dry. Actually, what we do is we have a network of about 200 hiring partners. We do fitment and performance based referrals wherever possible, and wherever applicable, actually. So we have an alum network of 27,000 folks, India and the US. We have our instructors who help us out in referrals, and we have a 200 plus hiring partners. I had shown the success metrics. So about the average salary growth that across the programs that our learners have seen after a transition, or after getting the role they were looking for, is about a hike of 18 or to 22 lakh per annum. So whatever was the base, hike on top of that, basically. Average, so the starting salary was 63 LPA to about 1.7 crore is what they're, 1.7 being the highest. Now, the three programs to quickly conclude. If you are unsure, talk to us about this. We would have either, the team would have either posted the link of the calendar to book a calendar slot with us, and talk to us one on one. It's free. Talk to us. We can help you with a path, a roadmap. For the forward deployed engineering program, it's 5.5 months. The transformative Gen AI Agentic AI interview lab program is 3 plus 3 months. The PwC Agentic AI Accelerator interview lab is 12 weeks plus 3 months of interview lab. Now, these are the pricing of all of the three. So the Agentic and uh, Accelerator and interview lab is 2 to 2.8 lakhs. Obviously, depends on the track that you choose or the role that you choose, and we have differential pricing for each. The transformative generative AI and agentic AI is 1.5 to 2.8 lakhs. The forward deployed AI engineering program is for 2.75 lakh. We also have a 50% refund policy. There are certain terms and conditions attached to that, so you can talk to our program advisor for that. We, on first come first basis, we do have some scholarships available, but for that, if they are available or not, you need to talk to your program advisor. They will be calling you after the session anyway, right? Lastly, all of our learners, like I said, they have personal commitments, they have families to look after, and we totally understand that. And therefore, we have various financial options, financing options available via easy EMIs, so that you can still progress and it doesn't burn a hole in your pocket, right? So I'm going to launch a poll to understand how many of you would be interested to get a call from us to particularly understand about our programs, and get a one-on-one personal AI career consultation. So go ahead, click on yes if you want to, and maybe if you want more details, you're not you want more details than what I've just shared. Yeah, Justin, over to you. Thanks a lot for letting me take a part of it.
All right, and let's get back to business. All right. So I think it's high time that it's enough with the slides and we'll get into the coding notebook. So we have the notebook here. I had shared the link with you already. Let me just share it with you once again. This is the link to the notebook, and this is the link to the data that we use to create the embeddings. Both of these shared in the chat. All right, let's get back. So here, what we are doing is we are starting with installing the required Python packages. I'm not going into each of the Python packages here. Superficially, it's mostly, okay, let me zoom in. You might require this. So our objective is to create a chatbot that answers questions about these documents that we have. And when the user asks a question, it should respond to that question based on the documents that we have here. And in order for that, we are implementing a RAG pipeline for the same. So we need a system that can answer questions about an insurance tech company, and the documents pertinent to the insurance tech company are these. Now, for this, we are using a RAG pipeline, and we are starting with the installation of the packages, starting with LangChain, Gradeo. Gradeo is to spin up a quick and dirty UI to test this application if you're interested in, and I'll show you that. And we are using OpenAI because we are using OpenAI LLMs because we need an LLM. And that LLM we are using OpenAI, if I remember, it is the GPT-5 or 4 or mini or something like that. You can change that if you want. And we are also using Plotly in order to get the embeddings plotted. We need to visualize it. We need to see how it looks like, even though in a three-dimensional space, it might not make much sense, but still we need to take a look at it. All right. So those are the package installations. And after that, we are using OpenAI's LLM from code. That means we need OpenAI API. So if you need access to OpenAI API, you need an API key from OpenAI. So you can go to platform.openai.com. Okay. You can go to platform.openai.com. And then within that, you can go to the API keys and you can create a new secret key and you can name it whatever and you can create the key and you can use the key. But you need to load some money into this because you can't use their API key for free. So you need to go to home and you need to load some money, probably like $5 or something, which is more than sufficient in order to even run simple applications from your end. Just letting you know that beforehand. So here, what I did was you can create an environment variable here. So in Jupyter Notebook, in order to create an environment variable, on the left of the notebook, you have this key button. Click on that. And then you can mention the name of the key and you can give the value here and you can enable the notebook to access it. Okay, perfect. Now, you can either do it that way or you can use this function which I used in order to make the user enter the API key in the coding notebook. Either way, I just found this to be easier, but from a production perspective, this is not recommended. All right, you need to keep it as an environment variable. Now, the OpenAI API key is input, and now we are importing. So this Google Colab. So this is a Jupyter notebook which we are running using Google Colab. So we need to make it access the data set that I was talking about. So what I did was that I downloaded the data sets, uploaded it to my Google Drive here. And then I just made the Google Colab file or the Jupyter notebook file access those documents from my Google Drive because this is also from Google. The files are also in Google Drive. So you can get it connected to Google Drive. And how you can do it when you run this cell, it'll ask for permission to connect this notebook to your Google Drive. And you can connect it and then access any files from your Google Drive. So just because I connected it to my Google Drive here, it doesn't mean that anybody can access it. So you will only be able to access your Google Drive's files from this. All right, don't worry about that. And then we are defining that we'll use the model GPT-4o mini and we'll create a database with the database name vector_db. You can change the name as per your requirement. And then here we are giving the file path. So this is the file path in my Google Drive. You need to change it accordingly for your Google Drive. Just letting you know beforehand. So in my Google Drive, it is under the folder IK materials to share, IK Launchpad 13 August 2026 tag within that LLM engineering main week 5 knowledge base. So I just gave the path to the folder. And we are mentioning that there are four different folders: company, contracts, employees, and products. Now we'll go to the main aspects. And the first aspect being, this KB root is the path to the directory. So the first aspect being, we need to load the files. So in order to load the files, what we are going to do is we are going to iterate through the folders inside this parent folder. So the folders inside the parent folder are, one moment, week 5, knowledge base. This was the folder. So the folders inside the parent folder are contracts, products, employees, and company. Now, it will automatically find those folders. The glob package of Python is used to iterate through the file directory structure. All right. Now, the next part. So this is a contingency. If folders are not present, what to do? That's all. Now, the next one, what it does is the add metadata function. So this add metadata function, what it does is it stamps a small metadata, which is the doc type key. So the doc type here is the folder name, like contracts, company, employees, products, etc. So for each document, we are also adding the metadata, which is which folder is this document from. You can have your own custom metadata. It can be the length of the file, it can be the name of the file, it can be any other information about the file that you want to add as metadata. It's totally your call. So this function is just used to add our custom metadata. All right. Now, this is just to tell that the files that we are going to read belongs to the UTF-8, so that if we get non-ASCII characters, it avoids crashing. That's all. Now, the main part. We are iterating through the different folders. And after iterating through the different folders, now we are going to fetch the document type. The document type is the folder name. That means contracts or employee or whatever. Now, after that, we are calling the directory loader function, which is an inbuilt function. We don't have to worry about it. And the directory loader function is going to take every element inside the folder, which ends with .md. And then we are using text loader in order to load these texts. And the text loader is used in LangChain in order to load the texts into a directory loader. And then we are passing any other additional parameter that is required, which we defined earlier, which is the encoding as UTF-8. So it simply means that fetch every markdown file from the parent folder and then read each with text loader using the UTF-8 settings. That's all. Now, after that, this actually reads all the files, producing a list of document objects, which is one document per file. So we haven't yet created the embeddings. We are just creating the document loader so that this document loader can be used in order to further create our embeddings. Now, there is this documents. What was the documents here? Yeah, documents is an empty list. So the documents list is extended using. So what we are going to do is we are iterating through the documents in the folder documents, and we are taking we are calling the add metadata function. We are passing the document and the doc type to it, and it is going to return the metadata infused document. So the document with the metadata infused is used to add to the list documents. So each document is taken, and we are creating a document with metadata out of that, and we are adding it to the empty list here. So that is what's happening here. Now, after that, by taking each document, we need to split each document into chunks. That is the chunking strategy which I was talking about earlier. So in order to perform the chunking, we are using the character text splitter, which is once again an inbuilt function. And the character text splitter, we need to mention the chunk size. We are mentioning the chunk size as 1000, and we are mentioning the chunk overlap as 200. If you remember in the previous example, I was showing you using the drawing a chunk size of 4 and an overlap of 2. Similarly, here a chunk size of 1000 and an overlap of 200. Now using that, we are going to create the chunks. And once the chunks are created, we are going to print the length of documents, the length of folders, how many chunks we created, all of that. Or did I switch it here? Ignore the warning and ignore any errors that you see, because recently LangChain has underwent another update so that it could throw some intermediate warnings or errors. It's fine, you can ignore it. So we have loaded 76 documents from the 4 folders that we have. The total number of chunks that we have is 413 chunks, because we ended up splitting the 76 documents in such a way that the chunk size is 1000 and the overlap is 200. And the types of documents that we have are 4 different types, because the types are the folder names. So this is what we did right now. We just chunked it. We haven't created embeddings yet. Now, the next part is to create embeddings and then to create the Chroma Vector DB using the embeddings. Now, we did say that the document metadata was already created in the previous part. Now we are initializing the OpenAI embeddings, and we are going to pass each chunk into the embeddings in order to create embeddings out of that. Now the next part here, this is creating the embedding client, and then the default OpenAI embedding model creates that 1538 or whatever that dimension size is. Now, the next part here. So here what we are going to do is, if the VectorDB folder exists from a previous run of the notebook, then open it, wipe it, and create a new VectorDB. That's what it means. So if the DB is already existing, then delete the collection is what we are saying. And if the DB is not existing, which is our case, we are running it for the first time, then what happens is we are calling Chroma, and we are asking Chroma DB to create embeddings from documents, which is what we saw in the slides, Chroma from documents. And we are passing the documents, which is our chunks. We are passing the embedding generator here that we initialized, so that the embedding generator can act on the chunks in order to create the embeddings. And then here what happens is, the chunks will be converted to embeddings, and the embeddings, which is the resultant vectors plus the text plus the metadata, all of the 3 are written into the Chroma DB collection. And the name of the vector DB will be persisted, and the name of the vector DB we already gave us vector underscore DB or something like that. So that is our vector store. And we are printing. The vector store is created with so many vectors, so many documents. So you can see here that vector store is created with 413 documents. Please ignore the errors that you see. That is because LangChain recently underwent an update. In the new variant of LangChain, there is some changes in the syntax, for instance. All right. Can you hear me? Okay. You can. Okay. Now, the vector store dot underscore collection dot count gives you the number of documents in the vector DB. So there are 413 documents. Documents actually refer to chunks. 413 chunks created out of 76 documents. That's what the concept is. Now, let's investigate the vectors. Let's take a look at the vectors. So we are fetching the count of the collection, and we are going to print the length of an embedding. We are going to fetch one embedding, and we are going to print the length of an embedding. So the first embedding is fetched with index 0, and we are going to print the length of that, and it comes out to be 1536 dimensions. Now we have 413 vectors with 1536 dimensions in the vector store. Now the next part is that we will visualize the vectors. We need to take a look at the vectors. So in order to visualize the vectors, I think this one was better for that. Yeah. In order to visualize the vectors, first, what we are going to do is, so what we are going to do is, we are going to initialize that. We need to fetch every record's embedding vector, the original chunk text, the metadata dictionary, everything in one single call. So we are fetching from using collection, we are going to get embeddings, documents, and metadata, everything together for every document. Now, in the vector that we created, so in the embedding list that we created earlier, that embedding list is converted into a NumPy array using this line of code. Because we need to use these vectors, or we need to use these NumPy arrays in order to populate it into a 2D graph. Now, we are also fetching the documents corresponding to it, and the metadata corresponding to it. And after that, we are initializing some colors. That's it. I see there are multiple hands that are raised. I'll come to you in a moment. Once I finish this, we can come to the individual questions as well. Now, what we are going to do is we are iterating through the different document types. We have 4 different document types. For each document type, we are going to give one color each: blue, green, red, and orange, respectively, for products, employees, contracts, and company. That is what we are going to do here. Now, utilizing all of these vectors, documents, metadata, colors, we are going to plot it. So if you remember, we are going to use something called TSNE, T distributor stochastic neighbor embedding, in order to convert this into 2 components, because you need to plot a 2D graph, you need only 2 components, X and Y. So you use TSNE to convert these embeddings into 2 components, which can be plotted on an XY graph. So we are initializing it in the first place, and we are applying this or transforming the vectors using that into 2 components. And then we are creating a scatter plot for this. And when you look at the scatter plot, it looks like this. It's the 2D vector store visualization. But please keep in mind that this is just for visualization. We are not converting the 2D or 3D for any operational purposes, just for visualization. And you can see that the red is one category, which is contracts. Blue is products, yellow is company, and green is employees. So you can see that there are some similarity, at least in a 2D space, there are some similarity between the products, contracts, company, but employees are quite distinct. So that is from a 2D visualization. So the same thing, instead of that, if we use a TSNE with 3 components, you can use it for 3D visualization. So TSNE with 3 components and 3D visualization looks like this. 3 dimensions. So this is a 3D visualization. So contracts in red, what was blue? Blue were products, orange were company, and green, the ones in green are employees. You can see that employees are still distinct to a good extent. And there is some, if you look at it from certain angles, even the blue and the red are distinguished sufficiently. And if you look at it from a different angle, all of the blue, red, yellow, everything is distinguished sufficiently. So I just wanted to let you know, the more the number of dimensions that you have, the more separation you will get between the different categories. All right. So don't use the 3-dimension or 2-dimension representations as an absolute representation, because you cannot see the actual representation in a 1500 dimensional graph. All right. Just letting you know. Okay. Now, oh, sorry. One more. Sorry, I got locked out of the system for some reason. All right. Now we are going to use LangChain. So this was visualization part, which was not a part of the operation. Now coming to the next part, which is using LangChain in order to stitch all of them together. Now, when you use LangChain to stitch all of them together, if you remember, I was talking about how LangChain works. LangChain works based on the concept of chaining. So we need to create each part of the chain and chain it together. So the first part is LLM. You need to initialize an LLM, and we are using OpenAI's LLM for this, which we already defined, the GPT-4 Omni. And there are some parameters called temperature and the model name. Model name is what model name that you want. GPT 5.2, GPT 5.1, etc. Temperature refers to how creative your model should be. Higher temperature means more creative. Lower temperature means more deterministic. So you can have a sufficiently high temperature so that it can use its reasoning capability whenever required, but not a very high temperature, so much so that it doesn't go completely creative, because you need it grounded on your documents. You need the responses to be grounded on your documents. Now, in order for it to remember the past conversations, so an LLM by default is not capable of remembering the past conversations. So in order for the LLM to inject the past conversation into. So in order to inject the past conversations into the LLM so that it can understand what happened until now, we are creating something called a conversation buffer memory. So this will create every past question and answer as actual message objects. And these can be exposed to the LLM so that the LLM will understand what happened until now. Now, that is the memory part. So LLM memory. Now the retriever. So we are initializing the vector store that we created, and we are initializing the retriever mod. We are telling that behave like a retriever. We are going to use you like a retriever right now. Now, there is an inbuilt function conversation retrieval chain from LLM, which can be used in order to build the full pipeline. That means in every turn, it is going to take a new question, plus prior chat history, which is injected into it using the memory, plus a retriever to retrieve the relevant chunks, plus an LLM to generate the responses. Everything chaining together into one single pipeline using the inbuilt function conversation retrieval chain in LangChain. Now, what happens here is when a user query comes, please explain what Ensure LLM is in a couple of sentences. Using the user query, we are going to trigger the conversation chain. So conversation chain, which we created here, we are going to invoke it using the invoke inbuilt function of that. And we are going to pass the user query as a question to it. And then what is going to happen is the user query along with the memory, that means what happened in the past, is converted to an embedding, and the embedding is compared, embedding of the user query is compared against the embedding of the documents in the vector DB, and the most similar documents are fetched, which is retrieval. And after that, the augmented query is created using the memory LLM, using the query memory, retrieved documents, and any system prompt, using which the LLM is triggered. And the LLM generates the final result. And we are printing the answer which is inside the result. And you can see here that Ensure LLM is an innovative insurance tech firm specializing in developing software products, all of the details. So these details, you wouldn't have got this answer if you just triggered a classic LLM. We got this information only because you got this response only because they had RAG. They had access to your documents. Just letting you know. So, okay. So we already discussed what happens here. It's the same thing. Memory and conversational chain. Now, the same thing, what happened here, we are going to wrap it inside a fancy UI, and we are going to use Gradeo for that. So Gradeo is a Python package that can be used to spin up quick UIs. So Gradeo has something called a chat interface. So GR is Gradeo. So we imported Gradeo as GR. So gr.chat interface. So Gradeo's chat interface expects a function with a signature, like something that takes a message history, etc. And it returns the bot's reply as a string. And then here what happens is we are going to launch a chat interface. And the chat interface, I have another UI showing for you. So the chat interface is available and you can click on this link and it is going to open up and you will be able to utilize the chat interface. You will be able to run the RAG-based pipeline, but the small change is that we'll be using a chat interface so that it looks fancy. So this is how the Gradeo UI looks like, nothing much. It has a provision to take up questions, which you can write here in the bottom and press enter. The question will trigger the LLM. Sorry, the question will trigger the RAG pipeline and it will do whatever it has to do and give us the answer. So I just asked to give details about the annual performance of the year 2022. So it gives the performance of the year, annual performance of the year 2022 for the different employees with the ratings for that particular year. And if you want to verify, cross-verify whether these answers are correct, you can just go to the actual information, which is employees, and you can check the details of each employee, and you will see annual performance history of each employee in 2022. This is what was occurred here. All right. So what we built is something very simple. A very simple chatbot which utilizes RAG, nothing fancy. And in order to support us with that, we use LangChain, which is the agentic AI or the LLM-based LLM framework that we used. And we combined the retrieval, the user query, embedding generation. We combined retrieval, augmentation, and generation in this. And to go into a bit more granular detail, what happened is user query comes in. User query is converted to embedding. The embedding of the user query is compared with the embedding of the documents which are present in the vector DB. The most similar documents are fetched. After that, the user query, which is text, plus the past conversation memory, plus the top documents which are retrieved, once again text, plus any other system prompt that you could have initialized. All of this together will trigger the LLM, and the LLM generates the answer, which is what you see here. All right. I just wanted to cover this part and also how the Gradeo looks like. That's it. So Gradeo is nothing but just a wrapper around this whole setup, so that you can take a look at how it's looking like using a UI. So inherently, what's happening is the same exact thing, just that the query will change every single time. So you have the conversation chain created using the LLM, retriever, and the memory. So this is what I wanted to convey. I know I did not go into the granular details of each inbuilt function which is used here. We only went into the granular details of the function that we wrote. So the other functions that are already available in LangChain, I superficially mentioned what it is. And if you're more interested in knowing about it, please go through the documentation and read more about these. So that is the code walkthrough that I wanted to give you today. I know it looks a bit simple. Yes, it is actually simple. But in order to understand what's happening, I first have to explain RAG in detail and then go into the coding aspects so that everybody's on the same page. I request to share this collab link. Okay, I thought I had shared this. One moment. Let me share it again. One minute. This is the collab link in the chat. And these are the documents. You might need these documents as well, right? You need to download these documents and add it to your Google Drive so that the collab can access these documents from which you can create the vector DB. So I've given both of these in the chat. So just click on this link that I shared with you. This is not opening in Collab. Just click on this link. It will take you to something like this. Now, for those who have already used Collab at least once in their Google account, you will see a button like this. For those who have not, just click on that. For those who have not used Google Collab, then you will have to click on the Open With button, click on Connect More Apps, and then search for Collab. And there is something called Collaboratory. Click on that and click on that, and you will be able to install it. It's already installed for my account. So for your account, please install it. And after you install it, you will see this option here, or in your drop down, you will see Google Collaboratory. Just click on that and it is going to open in Google Colab. Like this. I can show you one more thing. So if you haven't used Colab before, it might look like this for you when you click on the link, right? Now, what you have to do is click on the Open With button here, click on Connect More, check for Google Collaboratory here. If Google Collaboratory is not available in the list of applications, click on Connect More Apps. And inside the list, please search for Collab. And it will give you Collaboratory. Click on that. And this one with the icon CO, click on that and click on the button Install. And after the installation is done to your Google account, just refresh this. And when you refresh this, inside the drop down here, you will see Google Collaboratory. So you can just click on that and this file is going to be opened in Google Collaboratory like this. So this is for the folks who haven't used Google Colab before. And for those who are proficient, those who have already used Google Colab, just click on the, sorry. For those who have already used the Google Colab, so are you saying that you're only getting the share option? One moment, let me try opening it in incognito or something. Once you sign in, so let me just make a change to the permissions in that case. If the problem is with permissions, why is this not loading? If I give you edit permissions, the problem is that anybody will be able to make changes to this and then it'll be counterproductive for you guys. That's why I did not give the edit permission. Yeah, general access, anybody with the link. So it might open something like this and then file open. Or if you do not have this drop down, just go to file open. And if Google Collaboratory is available, click on that. If not, connect more apps, install Google Collaboratory, come back, and then
I
open
think
in
just in some
Collaboratory.
of them are able to access it. So I think the access is there.
Okay. Okay. So for those who do not have this drop down, just use the file open button instead. Perfect. Okay. Now we can take up your questions. I know you might have a lot of questions. There are a lot of questions in the Q&A as well.
Most of it I've tried to answer, Justin, so that because I know we are, heavily over time. We are almost half an hour over time, and I understand,
Yeah.
you still might have some part of your day available because you are, in time-wise behind us. So I've tried to answer most of it, and I think you explained everything in quite a lot of detail. And you can answer the questions if you one or two if you want, but I think we are also good.
Mhm. Yeah. So one of the questions was about a different model. The model by the name of one moment, let me just take the Q&A. The model by the name of Snowflake Arctic Embed XS. So Snowflake Arctic Embed XS is one very good model which is actually meant for embedding generation purposes. I use the term BERT only because BERT is one of the foundation models and BERT is one of the oldest models for such purposes. So many of you might have heard the name of BERT. That is why I took the name, that's all. Now, why not SQL or MongoDB? I think I already answered it. It is because the quick retrieval. So the vector DBs are meant for quick retrieval, especially using concepts like approximate nearest neighbors. So if you use SQL DB, you can perform a pairwise comparison with every element in your SQL DB and perform the retrieval, but that's going to take a lot of time. Here, we are not referring to scalable RAG. Krishna, you're absolutely right. We are not going to scalable RAG at this point. Okay. And can you use n8n? You can use n8n. N8n is mostly an event-driven system. So regarding n8n, for those who do not know, n8n is a UI-based system where you can develop applications which are mostly event-driven. So you can utilize LLMs as well. You can utilize RAG as well there. You can do all of these things, what I just showed you in n8n as well. And this is UI-based. By the way, in the IK curriculum, n8n is covered extensively. Why not use GUI for RAG pipeline building? Yes, that is what n8n is one example of that. So retrieval using similarity search returns chunks or documents, returns the chunks, not the documents. That is why I was saying that getting the right chunk is important, which is why proper chunking is very important. And using the chunk, you can fetch the corresponding documents as well. If you have mentioned the name of the document from the original set of documents, you can go ahead and fetch it. You can do that. But it is not recommended for a reason. Your document can be very big. Reading that complete document into the LLM might not be feasible. So chunking is required. How would the decision-making process go while designing such systems? There is a lot of decision-making. What embedding generation model do you want to use? Even the choice of RAG. So when you decide to use RAG, there is a small caveat. So the retrieved chunks are being fed into the LLM. That means if you're using an LLM, like for example, OpenAI's LLM, you are actually taking your data and giving it there, right? Do you really want to do that? So whether you want RAG is one question. If yes, how do you want to use RAG? What embedding generation model? What kind of chunking? What kind of tokenization? What kind of vector DB do you want to use? What tools do you want to incorporate into this? Do you want to incorporate something like MCPs, Model Context Protocol? A lot of design choices are there, which we want to address. Which vector DB is better, Pinecone or FAISS? Totally depends on what you're trying to do with them. So the answer is totally depends on what you're trying to do with them. If you're going to create something like a proof of concept, for instance, then I would personally recommend something like FAISS. So the idea of Pinecone is that it is actually fully managed. while in the case of FAISS, we manage it. So FAISS is free and open source while Pinecone is paid. So if you want something which is easy to use, I would say Pinecone. But if you want something which you have complete control of, which you wanna mess with in any way, which you want absolute liberty to, go for FAISS. All right. But whenever you handle open source or free stuff like FAISS, you will have to take care of a lot of things. For instance, when you want to scale it, we have to manage the scaling. When you have to take care of persistence, we have to manage the persistence. Distributed search, we have to build it. Any metadata filtering, we will have to do it ourselves. All of this. Is my understanding correct? Rather than passing whole document to ChatGPT, ask questions on which it will reach the context window, or RAG will help giving only the important ones. In a way, you are right. There is another thing. This is not one document we are dealing with. We are dealing with thousands or even millions of documents, maybe. In such a scenario, feeding all of this one by one to the LLM and trying to expect LLM to find the answer to the user query is not going to be feasible, which is why RAG is important. Now, is an embedding model an encoder only model? Usually, yes, because we don't need to generate text. We need to only convert the text into numbers. So, like BERT, for instance. So, how do we evaluate if our decisions are right? Good question. So, in an LLM-based application, there are also evaluation mechanisms. You can read about tools like Langsmith, Langfuse, etc in order to get more idea about evaluation strategies. And then you can also look into evaluation mechanisms, like there is something called LLM as a judge. You can use another LLM to judge the outcome of our LLM. You can even use ground truth data in order to calculate many metrics which can be utilized to see how good our system is. All of this. Can we learn vector database administration? I'm not exactly sure as to what you're referring to vector database administration, because vector DBs are usually created for a specific purpose rather than to store the data just like that. So if you want to build a chatbot which can perform um, semantic similarity search, you create a vector DB rather than just creating a vector DB to store your data just like that. Can we do all of this on our local setup? Of course, you can use a local setup. So you can use an open source model like Llama if you're interested. And you can use something like, what was the name of that? Ollama. This is not the name of a model. Ollama is a framework that is used to run open source LLMs on your own CPU or GPU. So you have a list of models publicly available in Ollama. OLLAMA. Now, these are the list of models, Llama 3.1, DeepSeek R1, a lot of them. So you can utilize them and you can run everything in your local system as well. We are sharing enterprise sensitive information to the LLM. What kind of guardrails are required? So that's actually a very detailed answer that I would go into. But superficially, first thing, is it all right to share the information with LLM providers? If not, then you will have to use your own, you will have to deploy LLMs in your own systems, and then you will have to utilize that. And then you can use a lot of guardrails with respect to personally identifiable information, redacting them, replacing them, etc. Not going into the details of that, but superficially, these could be the guardrails that you need to go into. What if the data has images? So there are a lot of models available out there which can create embeddings using images as well. So OpenAI's Clip is one example of that. So you can create text out of images, you can create embedding out of images, all of this. So images, audio, video, text, everything can be converted to meaningful embeddings if you use appropriate models. Is there a framework that could be used to simply set up knobs to simply configure and tweak the decisions while building such systems? We are evaluating the outputs using things like Langsmith. Of course, you can absolutely do that. I think N8N will also help you to a great extent since you are looking at a UI-based framework. How any data relation can be maintained in chunks or embeddings like table data. So the closest that these embeddings can come to a tabular data is because of the metadata. Each chunk can have its own metadata, like the file name, the folder name, the file length, or whatever the author name, or whatever else that you want to add to the metadata. So that can help you visualize the vector DB's data similar to that of your traditional tabular data. System prompts or guardrails, which one is feasible to control or prevent the PI data exposure? I would say both. So system prompts is good. You can ask the LLM to replace the PII data with something, but there's always a chance that the LLM might miss some of it. So in order to handle that, you can use guardrails, and some guardrails you can have your custom functions. Now, if you are interested in those guardrails, one example could be named entity recognition. Named entity recognition is used to find certain specific entities like people's names, location, addresses, employment details, date, etc. So you can use a named entity recognition pipeline from Python packages like Spacy, for instance. Spacy is a popular Python package which has named entity recognition capability. So you can just run the text through that in order to see whether the PII data was actually redacted by the model. If not, you can ensure that you do it using this pipeline. I would recommend don't overload your LLM because usage of LLMs comes at a cost. So why don't you utilize aspects like this in order to take care of the PIA data handling, for instance, so that it doesn't increase the cost, because utilizing LLMs always comes at a cost.
I think we have answered.
Right.
No,
I
no, that's
think
okay.
I took
Thanks,
up
Justin.
sufficient questions here. We still have
Yes, yes,
questions
yes.
coming up.
We will keep
Yeah,
having questions, but thanks for staying back. We are 35 minutes over time, and it's commendable how you always make sure every learner gets the right information out of your sessions. And thanks a ton for doing this over and over again, Justin. I'm going to thank everyone for joining in our audience also. Hope you had a great session. Keep joining us like this, and if you're interested to have a longer impact and keep doing such concepts across in a more structured manner, uh, have come and learn them from Justin and instructors like him in our program. So thanks a lot. Good night, everybody. Thanks a ton, Justin, again. Take care. Bye.
thanks everybody. Thanks for your time. Have a great
Recording stop.